can reach me. My Discord ID is Alisha Ling. Okay. Also can reach me at Gmail. Okay. So let's talk about van der Waerden's theorem. Okay. So this is basically a theorem that tells you something about arithmetic progressions. Okay. So what it says is that given any coloring of the natural numbers, with some finitely many colors, okay, there are arithmetic progressions of arbitrarily long length, okay, that are of the same color. Okay, so you're looking for monochromatic arithmetic progressions, okay, of arbitrarily large length, okay. So why is this interesting, right? This is interesting because, like, so for example, if you say something like no, by length I mean like a then a plus d, a plus 2d, up to a plus n minus 1d. Okay, so there exists some a and d, okay, such that these are all of the same color.
Okay, so you're telling that this n can be arbitrary.
Yeah. Okay, so n can be like 10 million or whatever you want. Okay. Okay, so the point is to think about why something is true, right? Like humans, whenever they see something is true, okay, you always ask, can you weaken the hypothesis, okay, such that the same thing is true, right? And kind of that leads you to this, okay, if you're looking for arithmetic progressions in the natural numbers, okay. So for example, people asked for arithmetic progressions in the prime numbers, okay. So this is like a very natural starting point of that, okay, right? Yeah, so this is part of Ramsey theory, okay. But yeah, this is like much more advanced than the usual Ramsey's theorem, okay. Okay, so yeah, so you try to ask, why is it true, okay, and what kind of hypothesis is like the smallest possible for it to be true, okay. So for example, people asked about prime numbers, okay, so are there arbitrarily large long APs in primes, okay. So this is solved now, okay. So this is called the Green-Tau theorem, okay. But then this was unsolved for a long time, right? So this is 2004, okay. The theorem that I'm covering is 1927, okay. So for a long time this was unsolved, okay, but people thought about it, And then they were like, okay, we cannot prove that there are arbitrarily long APs in primes. Okay. But primes are like aplenty, right? Like they knew that n by log n number of primes. Okay. Because prime number theorem is like 1900 in the start. Okay. So they knew about that the number of primes is quite large. Okay. Like the density of primes is quite close to n. Okay. So then a natural question to ask is that does it only depend on density, right? So if the density is close to 1, right, is positive in Q1, okay, then are there right? So even this is like pretty hard. No, Green-Tau theorem does not follow from van der Waerden. Okay. So if the density is positive, then are there arbitrarily long APs, right? So for example, if you look at well, stuff like some sequence with bounded differences. Okay, so that will have positive density. Okay, and then you can try to show that this will have arbitrarily long APs. Okay, right. So this was solved in 1970. Okay, so this is an easier question, right? I'm slowly getting to easier and easier questions. Okay, so this is what is called as Simonides theorem. Okay, positive density means that in any n numbers, there are some like 1 by 100 of them which are present in our set. Okay, so that there is some positive number, like in this case 1 by 100. Okay, such that that number times the number of elements that you're looking at, like the first capital N elements, there are like 1 by 100 of them which are present in the set. Okay. So that is like a loose definition of density. Okay, can make this more precise by taking n to be very large. Okay. Anyway, so you can just think of what I just said, like just that there is some constant, so that in every in the first capital N numbers, there are some constant times n number of elements. Okay, so this is also hard, right? Like this is 1970. Okay, so then people ask basically what I'm going to prove today. Okay, which is like what if you just separate the natural numbers into finite number of sets. Okay, so if we partition does one of them have arbitrarily APs? Okay, so this is the question asked by van der Waerden. Okay. Okay, so by the way, all of these are like, okay, I mean, Fields Medal wasn't there in 1927. Okay, but this is a Fields Medal winning work. Okay. This is a Fields Medal winning work. Okay, so all of these are very big advances. Okay, and all of them build on top of the other. Okay, so Semiradi looked at van der Waerden's proof. Okay, and then like he worked on it. Like this is quite a big advance, I would say. This is also quite a big advance, but more stuff is like in common. Okay. All right. So So let's talk about van der Waerden's theorem. Okay. So let's begin with a very simple thing. Okay, which is the n equal to 2 case. Okay.
Excuse me, sir.
Yeah.
Can you please once show the statement of van der Waerden?
Yeah.
I have a doubt. Like, what if we color all the primes red and all the composites blue? Then doesn't that imply that there would be a prime AP in primes of arbitrary large n?
No,
But there are already primes. I mean,
but we
there are
have no
already
control
APs.
about which color, right?
Yeah.
So there could be just composite, right? Like we don't have any control on which color will have the arbitrarily large APs.
Okay, I understood.
Right. So composites do have arbitrarily long consecutive stuff in them, right? It's not hard to show. So that's an AP. Right. Any consecutive numbers are an AP. Okay. So okay. So let's look at n equal to 2. Okay. So this just says that there are two numbers which are of the same color. Okay. So then I'll just call it VDW theorem.
N represent?
Hmm?
What does N represent?
N is
N
the
is the
length
number
of
of
the
colors.
sequence.
Ah, yes.
This.
Wait,
Okay,
N
actually,
is the length or
let me
number of
just
colors?
say it formally. Okay. So this is the finite version of the above theorem. Okay, so given any n, okay, there is a capital N, okay, depending on n, okay, such that okay, actually n and k, there is a capital N depending only on n and k, such that given any coloring of 1 to capital N with k colors, there is a monochromatic AP of length n. Okay, so is this understood?
This is a stronger version, right?
Yeah, so this is a priori stronger, but one can show that both are equivalent.
Yeah, it makes sense.
Okay, so I'll be proving this version. Okay, this will allow me some more control. That's the point. Okay. All right. So let's just talk about n equal to 2. Okay. So what does that mean? Right. Any two length AP is just like having any two numbers, right? So it's like basically equivalent to saying that there is a n for which there are two numbers of the same color.
It's obvious, right?
Yeah. So, I mean, if it's not obvious to you, then just think about it for like 15-20 seconds. It's a very easy application of pigeonhole principle. Okay, so there are k colors. Okay, there are like very large number of numbers. So after k plus 1 itself, there will be two of them which are of the same color, right? So in this case, n equals to k plus 1 works. Okay. So now let's look at n equal to 3. So now this is the first non-trivial step, right? So we want to prove that there is a n for which there are 3 terms in AP of the same color.
Why can't A be 2n plus 2k plus 1? N be 2k plus 1?
Yeah, n is can be anything larger than k plus 1 and can be k power k plus 1 also.
No, I'm talking for this n equals 3 case.
Okay, why?
Like we again have k colors, and we can suppose for the worst case we assume we are coloring each by 2. We are coloring all numbers till 2k with the colors. So at the 2k plus 1th color, the third color needs to repeat.
No, there are not 3 colors. Oh, okay. So you're saying, okay. So what is your coloring? So you're saying that these have 2 terms, but why does so you're saying that here there will be 3 numbers of the same color.
Yes.
But why will there be 3 terms in arithmetic progression of the same color?
Acha, okay, makes sense.
Right? In AP. Okay, so you want to show that there is a plus D, and A plus 2D, all of the same color. Okay, so think about it for a minute.
I think 2k plus 1 times k factorial should work.
Yeah, just think it through. Talk to yourself about your argument. Okay. And if it makes sense, then tell me.
Yeah, like 2k plus 1 times k factorial should work.
Okay, sure. So what is the argument?
So like,
How many colors are there?
Huh?
Are they key colors or are there?
Yeah, there are k colors, right?
Okay.
That is the
actually never mind.
yeah, go on. So 2k plus 1 times k factorial.
No, actually,
Okay. So when I said think it through, then you know.
If there are 2 colors, I'm getting something with roughly about 320 elements. 300 and 320. So basically what I'm doing is
Okay.
you divide into 64 groups of 5
Mm-hmm.
and you consider the first 33 and
Mm-hmm.
now if we're assuming for now that there's just 2 colors and now in the 33 there would be it would actually be 65 groups of 5.
Sure, that doesn't matter. Okay.
So what you do is you consider the first 33 groups of 5 and because there are 32 ways to color each group of 5, 2 of them must have the exact same coloring.
Yeah, so you have groups of 5.
Yeah.
And then you have 33 of them. And then 2 of them will have the same color.
Yeah.
2 of them will be identical basically.
Yeah. The coloring would be identical.
Yeah.
And now you
Okay.
consider the first 3 elements of each of those 2 groups.
Mm-hmm.
Now there's one case that all 3 colors are the same, then we'd immediately be done.
So you're saying that you look at the first 3 things.
Yeah.
Okay.
Of both of those 2 identical colors.
Yeah.
Now one case is that all 3 are of the same color, in which we are done.
All 3 are, yeah, sure.
Now one thing is now all 3 are different colors, so there'll be 2 of the same color because we only have 2 colors.
Yeah.
Now, so say those two colors are blue and red, and no, blue and let's say the same color is blue, and without loss of generality,
Okay.
let's say
So
first
blue is
element
like
is red.
this and
Yeah.
like this here as well.
Now we consider the fifth element of each of these two groups.
Mm-hmm.
Now, if this fifth element is blue, we'd be done.
Mm-hmm.
If it was red, both of them have red.
Sure.
And say one is the 7th and one is the 10th group, then we consider the 20 minus 7th group, which is the 13th group. So these groups form stuff like arithmetic progression in the groups
Mm-hmm.
as a whole. Now the thing is, in the last one, we consider the last element of the group.
No, so you look at this element and you look at this element,
Yeah.
and you're looking at some group which is like in the middle or something.
No, which is like the middle group might not exist, like if it's too conjecture.
So that's okay.
So you consider like the reflection,
Okay.
and in the reflection, either the first. So what happens is, let's see the first
Mm.
element blue of the reflection, then we'd be done.
Yeah, if this is blue, then we are done. Yes.
Yeah. So say it's red.
Mm.
Now similarly for the third element,
Yes.
and the last element should. Wait, the first two doesn't matter, but the last one should also be blue.
Uh-huh. Okay.
But but then we get the first element of the first group, second element of the second, and third of the third group form an arithmetic progression.
Mm-hmm.
So we're
Yes.
done.
Yes. That's very good.
It's 325, but that's a very weak method of bounding.
Yeah, but that's good. Yes. Okay, so now try to think about three colors.
I feel like something similar could be done. So like, but I'll figure out the details.
Mm-hmm. Yeah. So the point is that if you try to do it just for n equal to 3 or something, okay, you'll kind of, well, it's not great. Okay, like you won't be able to try like push it down to n equal to 2 or something. Okay, so the correct thing to do is kind of you okay, actually let me think. No, actually this is fine. Yeah, so just try to think about how the general argument will go, basically. So what is going on is that each time we are getting something, okay, so consider blocks of k plus 1. Okay, you have k plus 1, and then the next k plus 1, and then the next k plus 1. Okay, so your whole number line, you're dividing it into k plus 1 blocks. Okay, now the point is that each of them, there are some finitely many ways to color it, right? Each has some k power k plus 1 ways to color, right? So therefore, after some k power k plus 1 into, like after seeing this many plus 1 blocks, right? Two of them will be identical. Two of them will be identically colored. Right?
Yes.
Okay. So now what? Now you have these two blocks. Sorry. Which are identically colored. So if this is blue, then this is also blue. And then if this is red, then this is also red. Right? So the point is that we kind of take the reflection of one over the other. Right? So suppose that these were some distance apart. Then we look at this block here.
So in general, it'll be 2k plus 1 times k to the power of k plus 1 plus 1. Like something like that.
Okay. So now this will be of the, like this cannot be of the same color as these two, right? And this and this are red. So this will not be red. Try to think about what we can do now with this. Sorry.
I think that if we layer them down below each other into a grid pattern, we just want no lines.
What do you mean?
If you just layer them into a grid pattern,
Okay.
we just want no lines.
What do you mean by layered them into a grid pattern?
I mean, we have groups of k plus 1 and we just put them below down each other and we just want an absence of lines.
Well, you just that does that make sense? Well, sure, kind of. Yeah.
No, but then we wouldn't
But it's
also
not.
need like some diagonal kind of thing, right?
I mean, exactly what do you mean by lines, right? Like it's very
Like the first one in the first row, like 1, 1, then 2, 2, then 3, 3. That would also form AP.
Right.
So that's also
Lines.
not.
Oh, that's a line. 1, 1, 2, 1, 2, 3, 1, 3 is a line.
okay. So here's an idea. Okay, so suppose that, see, the point is that we took k plus 1 things here, right? So two of them will be of the same color, right? So the point is that there will be some, like if this is A and if this is A plus D, then whatever is A plus 2D, right? Then this cannot be blue, right? Right? But now, instead of just looking at this block repeating, okay, we can just look at a block of size like double, okay? Because then that will contain the A plus 2D as well, okay? And then this will repeat, okay? So I'm not saying that this exact block will repeat, but a block of this size will repeat, okay? So a block of size 2 times k plus 1 will repeat. Okay. So consider that block, right? So we take this block and then we get another one like this. Okay. And then this will be some B plus D, B plus 2D, right? But now this will be identically colored, right? If this was colored, let's say pink, okay, and this is also colored pink, okay. Okay, and this will repeat in how many? In like so there are k power 2k plus 1. Okay, yeah. So k power 2k plus 1 well, blocks of size this many.
Plus
Okay.
1, right? We also add
Yeah,
1.
plus 1 blocks. Right? So the block of this size will repeat. Okay. In this many blocks. Okay, so let's call this yeah, so let's call this as n1. Okay, and let's call this as n2. Okay, now what's the point of doing this? The point of this exercise is that you consider the reflection of this block. Okay, now this term cannot be blue, right? Actually, okay, so forget about this term. Mainly it's about this term. Okay, so C. Okay, so this is C is the reflection of A across B. Okay, so it's like 2B minus A. 2B minus A plus D. Okay, so this block cannot be pink, right? Because if it was pink, then these three things would be in AP, right? But now it cannot be blue either. Okay, and why is that? Because this A, B plus D, and 2B minus A plus 2D. Okay, pink or blue.
Isn't this a grid thing?
Hmm?
Isn't this just a grid thing? So basically, you're saying it will be a 3x3 hyphen cube in the end case. So we can just do this thing and we can extend it into third dimension if we want to do 3 colors, and then we will have the last corner will be neither red nor pink, blue nor green or whatever it is, and we can keep on doing like that.
I'm not sure if I follow.
I mean that over here we have cannot be pink or blue, so it will have must be green, right? I will just take this whole thing as a block. And
Yeah.
we can layer the block, well, not layer, we can just go down again and again, and you can do that 3 times, and will be not red, not pink, not green, and not blue, right? And
Yeah, so that is the idea. But now, like, how do you exactly say it?
Over here we have A, B, and 2B minus A, right? So now next what we do is we have C, what is it? We repeat this thing because we know that this thing will repeat, or something of the same form will repeat at least multiple times, right? If for some large n.
Something of what form will repeat?
Blue, pink, pink, and pink, not blue, green.
Okay.
So we know this thing will repeat for if we keep a large enough n, right? Because if it does not repeat, we can just use a different color pattern, and that will repeat. Right. And so we have that this the last the thing that would have we can do that twice, and then we can make a reflection again. And that reflection will have it have that key. It will have that it's not blue, it's not pink, it's not pink. And the corner, the last corner cannot be blue, pink, or green.
Yeah.
And we
Yeah.
can keep on doing that and again. So instead of doing 3 dimensions, we go into 4 and then da da da.
Well, I'm not sure what you're talking about 3-dimension and all, but I think your idea sounds correct at least. Okay, so so did everyone first of all understand up till here? Okay, so did you understand that this cannot be pink or blue?
Yeah.
Okay, so I want to hear like 2, 3 yes at least.
Yeah,
Yes.
it makes
Yes.
sense.
Yes.
Okay, because this is kind of like the next step will be kind of, you know, we'll go even deeper into this rabbit hole. Okay, so let's assume everyone got it. Okay, so I'll take this block. Okay, and I'll make this repeat. Okay, so so this repeats. Okay, so this is a block of okay, so this is a block of size like 2 and 2 or something. Okay, okay, so this repeats in k power n2. Okay, +1 blocks. Okay, so we are taking size n2 blocks, we're repeating them k power n2 times. Okay, +1. So it will repeat, like there will be some n2 size block, okay, which will repeat. Okay, and each n2 size block will have this kind of structure within it. Okay, okay, so now what do I want? Okay, so I have this n2 size block. Okay, and then it repeats. So now what?
We take reflection again.
Yeah, so you'll take reflection again. Okay, so you get a new thing. Okay, and now, so this is, let's say, so this is what I'll call as like n3 or something. Okay, so in n3 there will be some 2 blocks of size n2 which repeat. Okay, all right, so yeah, now what do I do? So you have this a1, b1, okay, and this thing, and then you had this some a2 and some b2, and then this thing, right? So now what do we do?
But the gap between A1 and B2 plus D, so we can repeat that, and that means the last last cell of the last column will be last row will be not of that same color.
Yeah, so the main point is that if you look at this, so this is, let's say, green, right? And this is also green, right? So you take the reflection of this across this, okay? And that will be like the corresponding cell here, right? This. Now my claim is that this cell, okay, so I'll just say it like here. Okay, so claim this, okay, this cell cannot be colored, whatever it was, pink, blue, or green. Okay. So try to see now why that is true. So it cannot be colored green is obvious. Okay. So try to argue for pink and blue.
Why can't we do the grid thing again? We can just place these on top of each other.
What?
Why can't we just place these on top of each other? Like,
what do you mean?
Like going, we go in three directions. Going down is increasing by B minus A, going left is increasing by D, and going up is increasing by C minus B. Whatever was the increase for green. Right? So like if we go any combination of these things repeatedly, that if we go up and down, that will still create a same sum. Up and down is the same thing no matter where you are. Right? I will still have the same difference. So we can create a line and then we are done.
Yeah, I mean, I suppose that that does make sense. Okay. But you can just be like, you can just explicitly say why this is, right? Like, it's not hard. Like, you just have that these three are in arithmetic progression, right? Then the first pink and the second pink of this, okay? Those three will be in arithmetic progression, like together with this. Okay, and then this first blue together with this blue, okay? And the cell that we are working with, this three will be in arithmetic progression, okay? So, so let me just say it like this blue, okay? This blue. Okay, so these two together with this make an AP. Okay, is that clear to everyone?
Yes, sir.
Yeah.
Yes.
Yeah.
Okay, and then the pinks. This pink, and then this. Okay, so these will also be in AP. And then similar, like green is the most obvious, okay, because it literally took the reflection, okay? Okay, so can you see that now this argument can be generalized, okay? And finally, you'll get a cell which cannot be colored any of the K colors, okay, without forcing arithmetic progression.
And then can't you do the same thing for higher end? Like you know that there exists a sequence of 3 from this. So we can just make a sequence of 3 instead of a sequence of 2. Right? So we started with 2 reds and a blue. We can start with 3 reds and a blue. And we can do the same sort of thing again.
Well, what sort of, what do you mean by same sort of?
Strengthen the bound, since this bound is a very weak one.
Sure, you can try to strengthen the bound, but again, strengthening the bound is again a field theory work. Okay, field medal winning work. Okay,
I mean, you can increase it by
so
1
it's
or 2
not that
numbers.
easy.
I'm pretty sure you can decrease the bound by 1 or 2.
Yeah, I mean, significantly increasing decreasing the bound is the main thing. Anyway, so it's not easy. Okay, like bound is weak, I agree, but it's not a simple thing like you just look at the proof and try to
What is the
simplify it.
thing for arithmetic progression of rank 3 in 2 colors?
So I mean, I'll
like, what's the minimum?
Oh, okay. You're asking me what is the exact bound?
11 or
I have no
11,
idea.
13 for 2 colors and 3 sequence.
I mean, you can do a computer search or something.
It's either 13 or 11, I think.
Okay, so like make sure you understand what's the next step going to be from here.
Yes. So why can't we, when I was saying for 3 n equal to 3, I mean n equals to 4, we can make double, instead of having just one block, we can make 3 blocks. I mean, 2 extra blocks.
Okay.
And then we make the fourth reflection block. Right? And we can say that that corner is not any of the previous colors, and we can do that same thing again and again. So aren't we done for
Yeah. So that kind of argument is what will work. Okay, I'm just taking it step by step. Don't we're not trying to jump the gun here. Okay. All right. So okay, so this is how N3 is defined. Okay. So you guys know what's coming. Okay, so I'll take this full 2 and 3. Okay, so this will be bounded by 2 and 3, right? So I'll take this whole thing and then I'll shrink it again. Okay, and I'll say that, okay, so now I consider this as one block of N3. Okay, and then I'll say that this will repeat again. Okay, and that will be my N4. Okay, so in general, what I will have shown is that for K colors, you'll get a bound. Okay, so something like K power K power K power K. Okay, so there will be a lot of K's here. Okay, will suffice. Okay, so remember I'm taking a K power N3. Okay, and then that is what I'll raise to the power of K. Okay, so some K times or something. Okay,
n+1 times, right?
yeah, no. This is just for n equals to 3. Yeah,
Oh,
I mean,
okay.
we're not even started. This is just for n equals to 3. Okay. So when I said prepare to look at some big numbers, I meant it. Okay. Okay. So for n equals to 3, a simple bound of K power K. Okay. K plus 1 times. That suffices.
So K tetrated K plus 1.
Yeah. K tetrated K plus 1 times. Okay. Okay. So now let's think about n equals to 4.
Start with the tree sequence. Yeah, okay, start with a sequence of 3 consecutive reds.
Mm-hmm.
You get something that's not blue. Right?
Okay, so what will you start with?
A sequence of 3 consecutive reds.
3, there may not be 3 consecutive reds.
Not 3 consecutive, 3 APA reds. I don't know what to call it.
Yeah, a monochromatic 3 AP.
Yeah, if you start with a monochromatic 3 AP.
Okay.
Okay.
Okay, so your N1 is now K power K power K power K. Okay.
Yeah.
Such a thing may not exist in 4 colors. If we only know that if there are 3 colors, you can find such a thing. But in 4 colors,
No, for 4 colors, we can do the same thing.
I mean, we've proven it for any number of colors.
oh yeah, right.
Right? I mean, we can just repeat this argument now, right? Surely, I've stopped at 3 colors. Okay, but we can just keep repeating this, right? We can just consider this whole thing as a block. Okay.
Yeah.
And then again, we can consider this reflection element. Right?
Yeah, got it.
Yeah.
Okay, so we start with red, blue. Let's say we start with 3 reds.
Mm-hmm.
The last thing must be a blue. Without loss of generality, obviously. I'm not saying red or blue specifically, but
yeah. So you're saying that you consider this N1, which is this many. Okay. And then you look at the 4th term in this, right?
Yes. Right.
Then you let's say it looks like this. Okay, so some A plus D, A plus 2D, and then you look at the A plus 3D.
Yes.
Okay.
And then I repeat this down.
And you're assuming that these 3 are all red.
Yes.
Okay. Then this cannot be red because we are trying to avoid n equal to 4. Right. So this is, let's say, blue.
So now we repeat this whole thing. down. We consider this whole block of color. And we repeat it down. We can do that by considering it a color, right? We can consider this whole thing a type of color.
Exactly.
Okay, and we can repeat this down 3 times. So we get another. We can do the same type of thing. You get 2 other below ones, and then the below that. Let us say it's B, right?
No, I understand it, but let others think about it.
Okay.
You got it. It's fine. Yeah, Bhairav, I think you were saying something.
Yes, no, I was just saying, then we sort of use the previous result to get this 3 times in an arithmetic progression, and then we get the next level, and so
Yeah,
on.
so we are using the n equals to 3 result that we just proved, right?
Yeah, but it might not, like this block may not repeat because you're considering any four block to be a color. So it might not be like this.
Yes,
No,
but
yeah, it will be like this, right? Like we proved that for any block of n1.
Yeah, so
There
there
is
is some block like this, but like to use the n equals 3 condition, you're taking a 4 block of APs and coloring them, right?
No, so the idea is this. So you look at this whole thing, okay? So this will be a block of size, let's say less than equal to 2, 1. Let's say I just take a block of size 2 and 1, okay?
Yeah.
Now, how many ways can this be colored, right? K power 2 and 1.
Yeah.
Right? So think of these as a coloring of the block, okay?
Okay. But then this exact coloring might not repeat, right?
Yeah, this one may not repeat, but some other one will repeat.
Yeah, but that one may not have a. Okay, right. It has.
It will, because
Okay.
in any N1, there is some 3AP.
Okay, makes sense.
Right.
Okay, so think of the block of size 2 and 1, okay, as having been colored in K power, like 1 of K power 2 and 1 ways. Okay. So by the result for n equals to 3, the blocks of size 2 and 1 will appear in a 3AP. Okay, so like there will be a how do I say this? There is a 3AP of the blocks of size 2 and 1, which are, and these are which are identically colored. Okay. Now remember, within each of them, any block of size 2 and 1, there is this structure present. Okay. Okay, what do you mean by this structure? This structure is this structure. Okay, this kind of structure. Okay.
So, like, do we now take 2 and 1 of those things and say that something like that should come thrice?
Yeah, so just like, okay, so like to just show you what kind of sizes is going on. Okay, so remember to get a 3AP of blocks of size 2 and 1. Okay, like there are K power 2 and 1 many colors. Okay, so you're taking K power 2 and 1 or K power 2 and 1, and then K power 2 and 1 times. Okay. Okay, so that's like some truly big number. Okay, and that is just your n2. Okay, All right.
So we're
Someone was asking.
tetration.
Huh?
So basically we're tetrating to tetration.
Yeah, but that is just the start.
Is
Now
it
I'll tetrate N2. Okay.
Is it gonna reach Graham's number eventually?
Yeah, it's going to be something like Graham's number, but
No.
not quite. Graham's number will be bigger.
What is Graham's number?
It's some truly big number. Let's just say. Anyway, so coming back to the point, within any block of size 2 and 1, there is this structure present, right? So therefore, if I copy paste it 3 times, okay. Okay, and then
So we basically consider the next one.
I'll scale it down a bit. Okay, so then you consider the next one. Okay, so these are all, remember, these are all identically colored. Okay, okay, and each of them have some AP. Okay, so so now what's the point? The point is that, okay, so these numbers, these may not be the same color. Okay, the point is this, that you consider this number. Okay, sorry, yeah, this number. So this is now some A1, some A2, and this is some A3. Okay, and remember A1, A2, A3 are in AP. Okay. Okay, because we have taken the blocks so that the blocks are in AP. Wait, what? Yeah, that's correct. Okay, so now look at this number. So can it be colored blue? No, because these 4 terms will be a 4 AP, right? We're looking to avoid 4 APs. Okay, now can it be colored red?
No.
Right, and that will also be a no because of this diagonal kind of thing. Okay, so this cannot be colored red or blue. Okay, so this must be colored some pink or something.
Yeah, so now we can just take a block of this size and make it one.
Yeah, so now we can take a block of this size, okay, and then make a 3 AP out of that. Okay, so remember, you're not trying to just repeat it. You really want to make a 3 AP, okay, such that they are identically colored. Okay, so remember, now the colors are truly big. Okay, like there are now k power n2 colors. Okay, and in fact k power 2 n2, because like the 2 n2 things almost. Okay, and yeah, so k power 2 and 2 number of colors, and you want a block of size 2 and 2 to repeat. Okay, so that therefore you'll need k power 2 and 2 tetrated k power 2 and 2 times number of and blocks of size 2 and 2. Okay, so basically what's going on is that your n1 is going to be chosen so that there is a monochromatic I'll say it in general, right? So n-1 AP. Okay, and this will be true by induction hypothesis. Okay. Okay, then the N2 will be chosen so that there is a monochromatic n-1 AP of blocks of size n2 and 1. Okay. And then you just keep going. Okay. Nk will be chosen so that there is a monochromatic n-1 AP of blocks of size 2nk. Okay, and then we'll be done. Okay. At that point, at this point, we are guaranteed to have k APs of length n, all ending at the same, say, k monochromatic APs. APs of length n-1, all having the same nth term. Okay, and all having different colors. Okay, so this is the main thing, that all of them have the same nth term and all of them having different colors. Okay. So can you like see why this is going to prove that there is a n term AP which is monochromatic?
Because for the sake of contradiction, you would need another color for that last nth position. So
yeah, so there are only k colors, right? But all of them have different colors, right? So the nth term, which is like common to all of the APs, will have one of those colors, okay, which will mean that it is a monochromatic AP, okay, with the previous AP of that color. Okay, great. So so that is the proof of van der Waerden's theorem. Okay. So first of all, any doubts?
So is there any motivation behind this thing we did? Is there any motivation behind this induction? Like,
so this kind of argument is called as a color focusing argument. Okay.
okay.
So the idea is to get like to force basically, right? Force some numbers of different colors. Right, and then we
Wait, I
repeat.
didn't actually get what color focusing is.
Hmm?
Can you just repeat what color focusing is?
So this kind of argument is called as color focusing. Okay. So what are we doing, right? We started with blue, okay, and then we said that this cannot be blue, right? So we have color focused this color. Instead of k possible colors, it can only now be k minus 1 possible colors, right?
Okay.
And then we said that, okay, now we look at this kind of structure, okay, and structure will repeat again, right? And now we looked at this new element, okay. This number now is more focused, right? It cannot be now blue because of this AP, okay, and it cannot be red also, right, because of this. Okay, so it cannot be two colors, right? And then you take that structure, you make it repeat again, okay, and then you get some new thing, okay, which is even more focused, right? So you're bringing down the colors one by one. Make sense?
Yes.
Okay, and here also it's the same kind of argument. Okay, anything else? Any other questions?
Are there handouts with just color forcing argument problems, like really tough ones?
Well, this is not really a Olympiad kind of thing. Okay, like there are applications of van der Waerden's theorem that you can find, but yeah, I mean, like you can find papers with color focusing argument. Like like I can link you to some papers, but like I don't know if you'll call them handouts.
Like a bunch of problems on just such things.
Well,
Like
okay, so the idea is that, so for example, like this kind of idea is like very reasonable to see. Like
I get that, but I remember there once was some handout, I think a Canadian handout on such type of
well, there
stuff,
is
but I
one
can't.
Reed Barton's handout on van der Waerden's theorem, but I don't really call that. It's not a very nice handout, I would say. Okay, like just has like very bare bones explanation of what is going on. So I first encountered it in his handout, but yeah, I had to think about it myself mostly. Okay, so I'll give you some flavor of some generalizations. Okay. So you can generalize it to like instead of looking at the number line, okay, you can generalize it to, for example, two-dimensional space. Okay.
Is it the one which Shreyan said? Like the line?
No, I was saying the same thing as number line
He's just trying to interpret my proof as some
Right.
something. Okay, so this says that given any number of colors, let's say any coloring of n2, okay, with k colors, there is a monochromatic triangle. Okay. And like what triangle? Okay, any given triangle. Okay, so like in fact, so let's suppose you are given any points, let's say P1, P2 up to Pk in the lattice. Okay, so my claim is that there is a monochromatic, so there are monochromatic points. Okay, Q1, Q2, Qk, such that so how do I say this? Qi is some translation, like some vector v. Okay, so this is like a vector of natural numbers. Okay, plus some constant, and this constant is also in
They're basically similar, right?
Yeah, similar to
Okay.
the points Pi. Okay.
I don't think I get what that means.
Okay, so that means that, let's say I just take a basic case like P1, P2, P3 is like this. Okay. Then what I'm saying is that, so obviously these three might not be of the same color in my coloring. Okay. But I'll get some large isosceles right triangle. Okay. Which looks exactly like this. Okay. So not just any isosceles right triangle. For example, this is also an isosceles right triangle. Okay, but I'll get it in the same orientation. Okay.
Can't you do this by considering it as a vector?
Considering what as vectors?
The shape.
Okay, and
right, so we can then say that we just have what we say a six dimensional a 6-dimensional 3 collinear points. If we have right?
No, I don't understand.
Oh, that doesn't.
Okay, anyway, so this is what is called as Galileo's theorem. Okay, so it can be proven very similar to van der Waerden's theorem. Okay. So I would recommend trying out the triangle case. Okay. And you can build from there to any points. Okay, just think about an okay, maybe not isosceles right triangle, but like any kind of triangle first. Okay, and it's like a very similar color focusing argument will work. Okay, and like first, of course, you need to say what a finite version of this is. Okay, so given any coloring of N2 should be replaced by there exists some capital N such that given a coloring of N cross N, okay, like 1 to N cross 1 to N, okay, with K colors, then there's some points like this. Okay. Okay, then let me say what further generalizations are. Okay, so for example, in van der Waerden's theorem, okay, so here I said that there exists some, okay, of the same color, okay, but for some color, right? Like it's not, we don't have any control for what color it is. Okay, if I give you, some explicit coloring, then you won't really be able to tell. Okay, maybe if I give you an explicit one, might be able to tell. Okay, but At least this theorem does not tell you which one. Okay. So for example, one natural question you may ask is that, okay, so the color that comes the most times, okay, whatever that means, okay, does that have a infinite AB? Okay. So that is correct. Okay. Like it is true, but this theorem does not tell you. Okay. And that will be true because the density of that coloring, okay, of that specific color will be positive. Okay. It will be at least 1 over K. Okay. If K, there are K colors. So, sorry. So if there are K colors, there will be a color of density at least 1 over K. And hence Similarity theorem will answer that question. Okay. Okay. And then what does green tau do? Okay. Basically, the point is that primes are not of positive density. Okay. Primes are of density 1 over log n, okay, which tends to 0 as n tends to infinity. So really what they had to do was they had to come up with a version of Similarity's theorem, which was kind of even like they had to refine Similarity's theorem, okay, to work with something which is slightly weaker, okay. And okay, so they proved a stronger version of theorem. Okay. They also proved okay, so this, I mean, I'm not sure if this was known before, okay, but they showed that given any polynomials, okay, so here I'm looking at linear things, right? So, but they showed that given any polynomials P1 of x, P2 of x, and so on, okay, with integer coefficients and stuff, okay, then you can find some x for which I think these are monochromatic, okay. So that is really insane, okay.
Wait, I didn't get what you said.
So I said that you can replace what do you have right now, right? You have a plus d, a plus 2d, and so on, right? A plus n minus 1 into d, okay. So suppose you're given some polynomials, okay. Let's say okay, so I think we also require that pi of 0 to be 0, okay. So you're given some polynomials such that they have no constant term.
Integer
Okay.
polynomials.
Yeah, integer polynomials. Okay. Then there will be some a for which a plus p1 of d, a plus p2 of d, like there will be some a and d such that a plus pk of d are monochromatic.
You can also do this by forcing.
Yeah, you can prove this also by color focusing.
Would this also hold in the 2D case? Like you have
Yeah.
point and there's something similar to it.
What do you mean by a polynomial, right?
Like in the 2D case.
Oh, okay, polynomial in two variables.
Yeah, two variables.
It
Like
should work.
I'm not aware. I mean, maybe there is something. Okay. But yeah, I mean, this theorem I know the proof of. I've proved it. Like I've studied the proof.
What
Okay.
about a density thing?
Huh?
What about a density thing?
Whatever.
What about the density thing?
What about the density? What thing?
That if you have a finite set which has density greater
Okay.
than 0.
Wait, can you just
This is just for colors. Like this is just for like for any K coloring, this will work. Okay. I
Can
think there are
you roll up
density
that?
versions of this. Okay. But I think yeah, I mean this might be true for any density stuff also. Yeah, in fact I think they proved this for primes also. They proved this. Okay. Or at least maybe not green tau, but like tau with some other student proved this.
Can you
Okay.
scroll up a bit to show the 2D results?
Yeah. Okay, so basically what I'm saying is that given any shape, okay, which can be represented on the lattice, I can get some similar shape, okay, like in the same orientation, but just scaled up, okay, which is monochromatic.
Okay, thanks.
Okay, so that's all this means. Like, don't worry too much about what this means.
Yeah, I was just confused since I thought there was something about
There's some, so this is like a translation, okay, and this is the scale.
No, I wasn't confused about that. I was because I was wondering where the arithmetic progression came here, and then I realized nothing about that.
Well, it will be, right? Like if you take these points to be consecutive points, okay, then this will exactly tell you that
I
you
thought
get
there might be something
an
about.
AP.
Oh yes. Yeah, got it.
Okay, any other questions?
I don't have any questions.
Okay, so I'll end with like a short, like quote unquote application. Okay, so this can be proven in other ways. Okay, but like since Reed Barton mentioned in its handout, I'll prove it. Okay, so this is a problem of Iran 2004. Okay, so says that define this bracket X to be main of the fractional part of X and 1 minus fractional part of X.
So basically the distance to an integer.
Yeah, distance to an integer.
Zigzag curve.
Suppose that.
Is that a zigzag curve or am I imagining it wrong?
What?
Is that a zigzag curve?
Yeah, it's like the fractional part. Okay, so alpha is some irrational number. Okay, and let's
The
say.
graph of the bracket X, which it is a zigzag.
Oh, I see. Sure. Yeah, that's a zigzag curve. Yeah. Okay, so yeah, so alpha is an irrational number. Okay, and epsilon is some positive number. Then you have to prove that there is an n such that this curly of n square alpha is less than epsilon.
So we want to show n square alpha can go arbitrarily close to an integer.
Yes.
So if we reach and let us say we can reach an epsilon dash, then we can also just substitute alpha by epsilon dash and it will still work, right?
Oh, can you repeat?
If we prove it can reach an epsilon dash, we can substitute alpha with epsilon dash and it will still work.
Oh, sure. I mean, alpha can be replaced by fractional part of alpha. That's not a problem.
Well, this distance will be at most n times the distance of n alpha. So if we take n such that n alpha is very close to an integer, then it could work.
Okay, but n alpha You'll
N
have
square
to
alpha.
control its distance by like a factor of n.
It should be N square alpha, not N alpha.
No, he's trying to multiply n alpha by n. The point is that you can make n alpha very close to an integer, but that closeness, does it depend on like n? Like, can you make it
Yes.
depend on n? That may not be true, right?
Yes, but apparently it's something like the distance can be upper bounded by a constant times 1 over n squared.
Okay. So if I take epsilon to be smaller than that constant, then you will have a problem then.
So as in a constant times 1 over n squared, so then if you multiply it by n, it becomes a constant divided by n, so it will go to
Yes.
0.
So if you multiply by n, you're fine. Yes. But you're multiplying by n square, right?
Yes, but if we have for n alpha first, then you multiply by, then it's only becoming multiplication by n.
Yeah, but it's multiplication by the same n, not arbitrary n. Like what you have shown maybe is that n alpha times some other m. That will be less than epsilon. Right? I mean, I'm not sure if I
Wait, n
understand.
equals 0, this works, right?
Huh?
Is n a positive integer?
Yeah, there exists some n.
Is n non-zero?
Non-zero, of course. I mean, I'm not asking something trivial, right? Like, it's not a trivial statement. Okay, so let's recall the proof that n alpha is arbitrarily close to an integer. Okay, so can someone tell me this proof? Okay, so let's say it's less than 1 by m.
We take the GCD.
GCD of what?
I mean, we do the GCD algorithm of n alpha. We take the GCD algorithm of alpha and 1.
Okay.
Right? And we're going to keep on getting it smaller and smaller. Right?
Why?
Because the GCD algorithm will make a strictly smaller value. And it can never reach 0 since alpha is irrational.
No, but I don't follow.
Like if you jump alpha steps.
No, but alpha is irrational. What do you mean by alpha steps?
No, I mean if you jump steps of length alpha.
Huh?
If you jump steps of length alpha.
Okay.
Right. So first of all, you always take the fractional part only. So as that you don't have to consider. Right. And then what you do is you can get it close to an closer to an alpha by 2 to an integer.
What?
You can get it closer to alpha by 2 by 2. Closer than alpha by 2
closer to alpha by 2.
Closer than alpha by 2 to an integer.
Can
right?
get it closer to alpha by 2.
Closer than alpha. Like if you have an integer, we take the range of alpha by 2 around it.
Okay.
Right. So alpha alpha cannot jump over that. Right. Alpha will have to reach some point within that range.
Sure.
So
okay.
we can multiply alpha by some integer so that it's within alpha by 2 of an integer.
Sure.
And we can repeat that procedure again and again and get it half and half and half.
No. What do you mean by repeat that process? Like just show me the next step. What do you do?
Okay, my next step, we get alpha by 2 and we multiply it so that it goes to alpha by 4 within an integer. And then we multiply, so I goes alpha by 8, and then we multiply, so I goes alpha by 16.
Oh, just the second step. What was the second step?
We have first we get alpha, we multiply it by an integer, so I goes within alpha by 2 of an integer.
Mm-hmm.
Then we multiply it by another integer, so I goes alpha by 4 within alpha by 4 of an integer.
Why can you do that?
Because if a number is within alpha by 2 of an integer, we can it is alpha by 2, something like k, which is smaller than alpha by 2, plus an integer.
Okay.
This multiplied by integer is k into an integer plus an integer. Right?
Sure.
And the difference between this and an integer is the difference between k into that integer and an integer.
Sure.
And we can get k to k by 2. Right?
Okay, I guess that. Okay, sure. Yeah, that will work. Okay.
I have a different proof.
Yeah. So that's the one that I was thinking about. You wrote it.
Yeah.
Okay, so the point is that you partition the 0 to 1 interval, okay, into sizes m partitions. Okay. So m minus 1 by m. Okay. And then the point is that if you look at n alpha for, like, if you look at alpha 2 alpha and then n alpha, okay, let's say m plus 1 alpha. Okay, then two of them will land in the same thing. Okay. Okay, and then you can subtract. Okay, so then you'll get this. All right. But now the point is that think of these as colorings. Okay. Colorings of an alpha. Okay. And then try to show. Okay, so you'll consider n square alpha. Okay. And then we color n in ith color if this n square alpha is in the interval I by n, I by m to I plus 1 by m. Okay. And so we'll have long APs, right? By van der Waerden's theorem.
And then in the long APs, one of them will because it's an AP, will eventually land in the interval m minus 1 by m to 1.
Oh, what?
Because of its long APs,
okay,
you can eventually force that if you have an AP of length m plus 1 or above, will land. Oh no, that may not be the case if the GCD is bad. Like if the GCD, okay, never mind, that doesn't work.
Okay, so the point is that, so what, let's just write it down, right? What does this mean? So this means that a square alpha, a plus d squared alpha, a plus 2d squared alpha, and so on. Okay, they're fractional parts all lie in I by m and I plus 1 by m, right? So we subtract. Okay.
I feel like we should pair A and A plus 3D and A plus D and A plus 2D and B. Because then the AD term will cancel.
Sure, that might also work. Yeah, that might work. But anyway, there's a simpler argument. You just subtract. Okay. So you get D squared plus whatever,
Is
2AD.
I'm kind of confused because isn't van der Waals over naturals? So how do we apply it here?
I just said, right? Color N with the ith color.
Oh,
If
okay.
this is true.
Okay, got it.
Right. So this is our coloring. Okay. Okay. So think of colorings not as, colorings, but as like some kind of properties. Okay. So if you have some finitely many properties, okay, then there will be a AP which satisfies the same property. Okay. Okay. So D squared plus 2AD times alpha. This is less than 1 by m. Okay. Then D squared plus, like the next one will be 4, whatever it is. I'll just subtract this from each of them, right? So you'll get 4AD alpha. Okay, then D squared plus 6AD. Okay, so in general, you'll get D squared plus 2K. So K times 2AD alpha.
Don't you just need the first two terms? I mean, first two terms? Yeah, but can't you just use the first two terms directly?
Why?
Because subtracting them again, we get 2AD alpha smaller than 1 by m.
Okay, so?
And then we can subtract that from the first one and we get it is smaller than 2 by m. And we can just cover for that by decreasing m to 1 by 2 epsilon.
Okay, that makes sense. Sure.
No, but
Okay.
shouldn't it be a perfect square?
What? He's arguing why D square is, right? Like,
What you
like
do is you subtract
these two,
4AD and
you
D
get that 2AD alpha will be less than
2 by
whatever.
m.
1 by m.
2 by m.
2 by m, I think.
Oh, right.
Yeah, something like this. Okay.
How?
It would be 1 by m or even.
No, it should be 1 by m because like
Yeah.
both are in the same interval.
Both are positive or whatever.
How does it happen again?
Okay, just think it through. I'm out of time, so I have to just finish. Okay. So he's saying that this is true, and then you subtract
Therefore, D
this from
square
this,
alpha is
so
also
you'll get D squared alpha.
so we're done.
Okay.
What was it going to be if you are using many Ks?
Yeah.
What was the proof going to be if you're going to
Well,
use many?
I was just going to say that like this is an irrational number, so I'll find K so that this is very small. Okay. So, and that's it. Okay. And that would imply that D squared alpha is going to be very small.
Yes.
Okay, so I think I'll end here. Okay. So thank you guys.
Sure.
I'll stick around for questions, but we can stop here.
Okay.
Okay.